Let's do one more example. Let's find the equation of a plane passing through 3 given points. So the key here is that when we have 3 points, in most circumstances, 3 points determine the equation of a plane. So if I have 3 points somewhere in space, in almost every circumstance, there will be exactly one plane that goes through those 3 points. Okay? Now there is an exception. If the 3 points are collinear, so that they all lie on the same line, then they do not uniquely determine a plane. Because there are many planes that could go through these 3 points. For example, this plane goes through the 3 points, but also so does this plane. Okay, so generally 3 non-collinear points determine a plane. Okay? Okay, so we know that to find the equation of a plane, we need 2 pieces of information. We need a vector normal to the plane, and we need a point on the plane. Now, on that second count, we were good. In fact, we have more than enough information. We know 3 points that are in the plane. Okay? The trick here is going to be finding a vector normal to the plane. So here's what we're going to do. Here's how we're going to handle that. We're going to find 2 different vectors parallel to the plane. So maybe we could find this vector and this vector. We can do that by subtracting different pairs of points. Notice, by the way, there's lots of ways to do this. I could go this way, I can go this way, I can do this vector, I could do this vector, I could do, right? I have lots of ways that find 2 vectors parallel to the plane by just looking at those 3 points. All I need is 2 vectors. So we're going to grab any 2 vectors, distinct vectors, that are parallel to the plane. Now, if I can find a vector orthogonal to both of these vectors, the vector must also be orthogonal to the plane, right? That's the thinking. So I want to find a vector that is orthogonal to both of these vectors, and therefore orthogonal to the plane. And we have a trick for doing this. If I can find this vector in the plane and this vector in the plane, then by taking the cross product, I get a vector orthogonal to both of these vectors and therefore orthogonal to the plane. So that's the plan. Find 2 vectors that are parallel to the plane and take their cross product to find a vector normal to the plane. Okay, so I'm going to label my 2 vectors u and v. And to find a vector parallel to the plane, I'm going to subtract 2 of these points. Now I've got lots of pairs of points to choose from. Doesn't matter which pair I take. So let's say we take the first 2. Okay? And say I want to end up here and I want to start here. So end minus start. I'm going to take point -311. And I am going to subtract point -2, -3,1. And so that'll give me a vector pointing from this point to this point, and therefore parallel to the plane, since it's pointing from a point in the plane to a point in the plane. And so doing the subtraction, I get -3 minus -2, that's -1. 1 minus -3 is 4, and 1 minus 1 is 0. So that's one vector parallel to the plane. Let's do it one more time. I need two vectors that are parallel to the plane. So I've looked at this pair of points. Let's look at a different pair of points. Maybe I'll look at this pair of points. Okay, so again, end minus start. So -3, -1, 0, I believe it was. Let me double check. Yep. Minus -2, -3, 1. And subtracting these two gives me a different vector parallel to the plane. I get -1, 2, -1. Okay, so now that I have two vectors that are parallel to the plane, I'm going to find a vector orthogonal to both of these by taking their cross product, and that will be my normal vector. Okay, so to take the cross product, I'm going to take the determinant of a matrix where the first row is ijk. The second row is vector u, -1, 4, 0. And the last row is vector v, -1, 2, -1. And I'm just going to very quickly take this cross product. For component I, for the first component, -4 minus 0, so I get -4. For j, if I take the 2 by 2 of what's left, I get 1 minus 0, so that's 1. But since it's the j component, I switch the sign, I get a -1. And for k, I get -2 minus -4, so that's -2 plus 4, that's 2. So that gives me a vector orthogonal to both u and v, and therefore normal to the plane. And so now I have a vector normal to the plane. I have points that lie on the plane. I have everything I need to find the equation of a plane. Okay, so the equation of a plane, using the form ax minus x naught plus by minus y naught plus cz minus z naught. ABC, equals 0. That's very important. Can't leave off the equals 0. A, B, and C are the components of the normal vector. And x naught, y naught, z naught are the components of a point in the plane. Any one of these 3 points will work. Okay, so let's start plugging in. So A is -4 times x minus x naught. Let's just use the first point here. So -2, -3, 1. So first component here is -2. Plus B, -1. Y minus the second component in the point is -3. Plus last component in the normal vector is 2. And z minus and z naught. Z naught's the last component in the point, which is 1. Equals 0. And I'm just going to tidy this up a bit. -4 x plus 2 minus y plus 3 plus 2z minus 1 equals 0. And I'm going to leave that as my final answer. That is a point that goes, or I'm sorry, a plane that goes through all 3 points. All right, let's go ahead and check that graphically. So our 3 points are -2, -3, 1, -3, 1, 1, and -3, -1, 0. I've got my 3 points there. Okay. And our plane is -4 x plus 2 minus 1 times y plus 3 plus 2 times z minus 1 equals 0. And we could see that our plane does indeed pass through all three of those points.